Okay, so first of all, before we move on to the Maple part of the demonstration, let's look at that problem with when you have isobars, right? The curves with the same pressure. So this is one example from the homework. Um, like I said before, each line it's pretty irregular, right? But again, it represents the region of the function for which the value is the same, right? In this case, the function is the pressure at each point. So it's a function of two variables because the input is the geographical coordinates of that point. And then each line indicates the same value. I mean, the points for which you have the same pressure. So let's look at, for example, what happens around Vancouver, given by this point V and San Francisco. So um, I can pretty much estimate the pressure at the points. So once I have a good enough sample of these level curves, I can kind of estimate the value of the function at nearby points. Like if I look at the distance, if I look at this line here from 1008 all the way to 1016, on this direction toward Vancouver, um, it seems like the isobar is gonna drop. I mean, I'm sorry, the pressure drops by 4. Um, excuse me, increases by 4, right? So from 1008 to 1012, 1015. So um, V is kind of in between, maybe a little bit more than halfway through, right? On that step size of 4, if you want. So clearly it's going to be, I would say, maybe 118 or a little bit more than that, right? Or maybe, yeah, maybe 118, right? Kind of like in between two nearby isobars, between 1016 and 1020, which is not given here, not labeled. Whereas San Francisco is kind of exactly in between. Again, the two isobars. So it's going to be the middle point between 1008 and 1012, which is in this case 1010. As to where the winds are strongest, is it San Francisco or Vancouver? Obviously, San Francisco, because the isobars are closer together, so the drop in pressure is um, more sudden as you um, move around. I mean, as you look at the neighborhood of that point at San Francisco. So with that, let's go to the Maple demonstration here. I already sketched some of these things. Let me actually let's actually clear this up so that we can run them one more time, see how they pop up. So for each of these examples, I want to sketch the function in 3D. So I'm talking about the function of two variables first, for which we have we can sketch the graph of the function as a surface, right? So the domain will be in the xy plane, and then the value of the function on the z-axis. So z equals f of xy is going to be a surface. Level curves will be, again, when you set the function equal to a specific number, and then you look at the curve corresponding to that equation here. So let's do this for the function square root of 4 minus x squared minus y squared. This is going to be a hemisphere. We did that in the written part before. What I want to emphasize is, again, if you look it from above, so if you rotate the image from the perspective of z-axis and above, so if you superimpose it over the xy plane, you should see the domain of the function. Because remember how this function is constructed, right? So I mean, the domain is evaluated at the function, and for each point you're going to calculate the z value, and then that's going to be the point on this hemisphere. So if I whatever the graph of that function is, if I see it from above, it should overlap, it should project onto the domain of the function itself, which in this case is a disk of radius 2. As for the level curves, I already wrote here, let's say I want to see the region for which the function is equal to 1. If you do the computation over here, that's going to be a circle of radius square root of 3. So level curves will be in the shape of concentric circles. Maple uses the function contour plot to sketch level curves. You can control how many level curves you want to generate. In this case, 20. Oops. And the nice thing with Maple is if you scroll over these level curves, it will tell you what the value of each of the function is on that curve. Kind of like with the color coding as well, as you move toward the redder and redder curves, that means the value of the function is larger and larger. This is the example we did in class. I mean, in class, in the written part, square root of xy. This is the graph itself in 3D. And remember, the domain in this case was given by the first and the second quadrant, minus 2, 2, minus 2, 2. And oops, slip my hand here. So again, if I rotate it and see it from above, I should see the first and the second quadrant between minus 2 and 2 as the domain of the function. And this is the actual graph. And level curves, each of them is given by two pieces, right? So for example, 0.0952 is here and here, right? In the two quadrants. Always remember that the graph of a function of two variables can be a recognizable surface. When you set z equals f of xy, if you manipulate the terms, you may recognize again the shape just like before a sphere, or a more common one, a plane. Let's say the function is x plus y. If you see it as z equals f of xy, z equals x plus y is nothing but a plane that goes to the origin 0, 0, 0 and has a normal given by 1, 1 minus 1 in this case, if you remember the equation of the plane. So indeed, if we sketch it, you see a tilted plane like that. Again, that's the graph of the function. The domain is going to be actually a square. X between minus 2 and 2, y between minus 2 and 2. It's a square. So if I see it from above, this graph, it should project completely onto that square between minus 2 and 2 for each side. And the contour plots will be straight lines. Pretty obvious, right? If you set x plus y equal to a specific number, those will be straight lines, right? So this is, for example, where 2.43 is located. I mean, all the points on this line, if you plug them into the function, it'll give you, 2 whatever it was, 43, right? And let's finish with the level surfaces of a function of three variables. Like I said, in this case, things are a little bit more vague because you cannot see the function itself. You can only visualize the domain, which in this case happens to be a solid of radius 3. When you set it equal to a specific number, all you get are spheres, right? So for example, this is the sphere, the level surface corresponding to the value 1.2. As I increase the value of the function, the radius of the sphere actually decreases. I mean, if you set this equal to a larger number, when you solve for x squared plus y squared plus z squared, you get a smaller number. So that's why if I increase the value of the function and I look at the corresponding level surface, you get smaller and smaller spheres. The largest possible value of the function will be 3. And that happens just at the point 0, 0, 0. So as you come close to 3, let's say if I want to look at the function for which the value is 2.9, that's going to be, as you see here, a very tiny sphere. And if it's exactly 3, the level curve reduces to a point, right? That happens only at the origin here, 0, 0, 0. Okay, so I think that's it for this class. I'll see you next time. See you later.